The next talk is an atomic Hong-U-Mandel experiment. And the talk will be given by Denis Boiron from Institut d'Optique in Orsay.
This one and
this advances it.
No.
Okay.
Okay, so first I want to apologize for the white stuff in my nose, but if I get it off, I think you will have a quantum jump to a flow of blood, so I will keep it. So I want to thank you, thank the organizers to giving me the opportunity to talk about our research on the matter wave analog of the Hong-U-Mandel effect with ultra-cold atoms. So this work has been done at the Institut d'Optique in Palaiseau, France. And the main contributors were the two PhD students, Rafael Lopez and Almaz, and Rafael just defended a few months ago. And you have the old guys, and Pierre is a new PhD student. So this work has been published in Nature last April. So this work is part of quantum optics and quantum information processing field. So we introduce briefly this, and after, of course, describe the original experiment made by Hong-U and Mandel, and the way we have observed this effect and some conclusions. So quantum information processing is a field where you want to use several atoms in a superposition of several atoms to perform efficiently some tasks. So at the heart of quantum information processing is entanglement. And so this story started in 1935 with the famous paper of Einstein, Podolsky, and Rosen that wrote that type of question. And we have to wait a long time since Bell in 1963 demonstrate yes, that indeed there are some quantum results that you cannot reproduce by any classical methods. On the experimental point of view, I point out a few experiments. The first one in 1956 is considered by some as the birth of quantum optics, when Henry Brown and Twist, two astronomers, showed that if you use a sun or a discharge lamp, even if this source is completely chaotic, the photons are not independent due to quantum statistics. They want to be bunched. If they were using fermions, they would have observed anti-bunching. And after, in quantum optics, you use a non-classical source. So the most widely used, probably the one I will explain, and it was shown for the first time by Boiron and Weinberg in the 70s, that you can have a source creating pairs of photons that have really quantum behaviors. And obviously, the other experiment I want to show, the one in 1987 by Hong-U and Mandel. So in our team, we observe the Henry Brown and Twist analog in 2005 for bosons, 2007 for fermions, and we also observed the equivalent of this experiment in 2007 too. And now it's the 87 one. So as I said, we need a non-classical source, and the most widely used is this one. Let's use a pump, shine on a nonlinear crystal, Chi2 nonlinear crystals, and you have pairs of photons, usually called signal and idler. Depending on the symmetry of this crystal, either you see pictures like this or like this. What Boiron and Weinberg did is they put a detector somewhere and put another one and move another one somewhere else, and they're looking for coincidence counts. They have a background coincidence counts, but if they put the second one at a specific position, they have an enhanced count, demonstrating the existence of pairs of photons. And the two detectors should be at the phase matching condition for this to happen. Now, using this, what is the Hong-U-Mandel experiment is a basic building block of quantum information processing, meaning you take two atoms and you want to mix them on a beam splitter. So let's take two photons, a blue and a red, on the 50-50 beam splitters, I have 4 different possibilities. Each photons can be either reflected or transmitted. So if I'm looking the coincident counts between the 2 detectors, I have everything is equiprobable, so I have 1/2. No big deal. But if now I have 2 red photons, I still have my 4 cases, but the 2 on the top, I cannot distinguish them. At the quantum level, they're indistinguishable, and if this is the case, the quantum mechanics say that you have to be careful. In order to calculate the probability, you have first to sum the amplitudes, and after take the modulus square. And it happens that if you do that, the amplitudes are equal, but out of phase. And this pi phase difference is mandatory for a beam splitter in order to conserve energy. This means that this probability is 0. So even if each photon can be either reflected or transmitted, if you have 2 photons, they cannot emerge like this. They both going either this way or this way, and in fact, it's a fully entangled state in the Fock basis 2, 0 plus 0, 2. So it's a fully quantum entangled state. So how they did this? So you can recognize a few things: my pump, my nonlinear crystals, signal idler, mirrors. They have a beam splitter here, and they have detectors, and are looking for constant counts. And they add a clever trick is that they move the beam splitters. If the beam splitters is in the symmetric situation, the photons will be, in principle, detected simultaneously, whereas if the detector is up and down, 1 photon will arrive sooner, so you can know if it was reflected or transmitted, meaning that the photons are no more undistinguishable. So this was a knob to tune the indistinguishability in their cases. And they see what we want to see, meaning they have a constant counts if they're out of the symmetric situation, but when they're at symmetric situation, this constant counts drops drastically almost to 0. So this is a 2-particle effect, a really 2-particle effect, where you have 1 atom in each beam. I will come to that a bit later. And you see they have to be a bit careful because they did pinholes, interference filters, and so on. And we'll have to do the same with atoms in our experiment. So why do we want to do this with atoms? First, because it's fun. Second, because quantum information processing is a big thing, and you don't know if everything you want to do will be performed with the same platform, let's say photons or superconducting circuits and so on. So it's always good to have another platform. Atoms are good because they can be boson fermions, they have a lot of eternal states, and using ultra-cold atoms, we have the controllability, tunability, and the strong nonlinear effect because atoms interact strongly with one to the other. What is less good, or a bit unknown, is can we create pure quantum state, or do we have thermal effects somewhere? This is an open question. And also, the manipulation is obviously more difficult. We have to be in vacuum, and you need to find equivalent to mirrors, beam splitters, pinholes, and so on. So there are several. So I will use pairs. So there has been several demonstrations of pairs of atoms. I won't not give all of them. We have a talk on Friday on this type. On this type, in elastic collisions. In our experiment, we have used the first one, 2007, just a stupid thing to make 2 condensate collide. But the scattered atomic field happens to be highly non-quantum, in fact. But I will discuss these other techniques that we developed in 2013 a bit later, an exotic type of collisions. But I also have to choose an atom. In our case, is metastable helium atoms. So metastable state is this one. It's populated from the ground state by a plasma, and it's nice because you have optical transition to cool the atoms and manipulate it. And why do we choose these atoms? Because of these numbers. This is 20 electron volt. This is a huge energy, meaning that the metastable helium atoms will lead to ionization if it hits almost anything, and this can be used to an efficient detection by electronic by macrochannel plates. So the idea is that we have an experiment, we switch everything off, the atom will fall, they have very small velocity, so due to gravity they will fall on the detector, which is 50 centimeters below the trapping region, and we detect atoms one by one. I won't explain this because most of you know that. We can know the arrival time of that detector, which is 8 centimeters in diameter, and we can know the arrival position on these detectors. We know the value of gravity, meaning that knowing arrival time and arrival position, we can know the initial velocity because the initial size of the clouds are typically negligible. So what we measure is the three-dimensional velocity of the atoms of single atoms. And once you have a single atom detector, you can do whatever you want, and I will measure either one-body properties, the momentum distribution, or two-body properties, correlation function of that kind, which is related to probability to detect one particle at velocity v, knowing that you have detected another particle at velocity v prime. Okay, now the collision. In free space, if you have the dispersion relation is just parabola, energy is kinetic energy, so p squared by 2m. But if your atoms are embedded in periodic potentials, you will have bands. So let's say this is, for instance, the fundamental bands, and it happens here that if you have two atoms at a quasi-momenta k0, it could lead to a collisions, one going to k1 and one going to k2, because this fulfills the energy and quasi-momentum phase conditions. This is completely forbidden in free space unless k1 equals k2 equals k0, which is stupid. But this happens for a given range of k0, depending on the parameters of the lattice and so on. But it happens, so it will happen spontaneously. So this process will create pairs, k1 and k2. So this was pointed out first by Klaus Malmer in 2005. This was the first demonstration by Ketterle's group in 2006. So how it works, we have our condensate confined. We shine two laser beams that will interfere and produce a standing wave, but they're not exactly the same frequency, meaning that this standing wave is moving. But in the lattice, the frame of this moving lattice, the condensate is moving. That's a clever way to put the condensate at any velocities because the speed of the lattice is just related to this frequency difference. And if we do this, we indeed observe two peaks, one at K1 and one at K2. What is nice with this is that by tuning the frequency difference, we tune K0, and so we tune K1 and K2. So this is experimental data, the points, and the dashed line are the theoretical predictions. And since this process does not happen in free space, you can control the population in this mode K1 and K2 by just changing the duration of the lattice. So we can go from a low population to a very high population, high for quantum cold atom systems, meaning a few thousands. And so now we are almost ready to do the experiment. We have pairs of atoms. This is a zoom of the real data we have using for the home experiment. And the pinholes, in our case, because historically they are only two detectors, we have a specially resolved detectors. So the pinholes we don't have to add something. It's for free because just have to only look at numbers at a given position or in momentum space. We have this. It's non-classicals. At least we have pairs because we have as Bernard Weisberg an enhanced probability at the good position. And it's non-classical because we also have autocorrelation functions, and we have shown that this source produced is non-classical because it violates some classical inequality, such as Cauchy-Schwarz inequality. So we have a good source. Now we need mirrors and beam splitters. And this is a well-known technique in atom interferometry. We use a two-photon transition, Bragg diffraction. So you absorb a photon and you emit stimulatedly another photons. So you exchange the photons, and so you can, in this way, have transfer atoms from a given momentum PA to PB, knowing the wave vector difference and the frequency difference of these two laser beams. And it's a coherent process. So Rabi oscillations between the two states A and B, meaning that if you stop the Rabi oscillation where you have full transfer, you have a mirror. If you stop the oscillation where you are half, you have a beam splitter. And so now we have everything. So the experiment is like this. We have a condensate. We shine our two lasers to make the lattice, to create the pairs, A and B. And after, we switch everything off. So they have different velocities. So in the position-time diagram, they will move. Okay, they will separate. So at a given time, T2 will apply the other beam for Bragg diffraction in the mirror situations. And this flips the velocities of A to the velocity of B. So in the raised frame, you have this, you split. So the trajectory we recombine at a given time, T3. And now our analog of the moving position of the beam splitter from Hong-Ou-Mandel will be in the time analog. If we apply another time the Bragg diffraction at the beam splitter situation, if we apply it at exactly when the beam overlap, we will have indistinguishable atoms. If we apply it before or later, we have distinguishable atoms. And to make the long story short, and after we detect everything on our detectors, and we calculate the correlation functions, the coincidence count. And this is what we observed. So we have, in function of this, the delay between the second Bragg diffraction beam, we observe at the given duration, time, delay, that indeed we have a drop of the coincidence count. And we can define with this formula a visibility of 0.65. So is this the Hong-Ou-Mandel effect, or can we explain it differently? If you say that atoms are classical particles, they do not care about the time where you put these beam splitters, so you should have something straight line. So it's not classical particles. But could it be waves? Here it's a bit more subtle, because indeed, if you use wave, you could have a dip. But you can show theoretically that this dip cannot be very deep, and the visibility, the maximal visibility with waves is 0.5. And this is the red area here with our arrow bars. And so the fact that we are below this is a proof that we indeed observe a two-atom interference, an atomic Hong-Ou-Mandel effect. Are we happy? Yes. Are we totally happy? No, because it's not zero. Why? I don't know what this is. Okay, so there are several reasons. First one said, okay, you put the beam splitter at the good timing, but the atoms are not totally indistinguishable. This means that the contrast is non-zero. We do not believe this because, in fact, you can calculate the visibility at the output of the beam splitter if you know the correlation properties before the beam splitters. You have a formula here. If your particles are indistinguishable, you can calculate that. And as I show you, we have measured all these numbers. So you can just plug the numbers, and if you plug the numbers, we find 0.6. What we have measured experimentally. So to a signal to noise ratio, okay, it's not perfect, but if the atoms are not indistinguishable, they're not that far from that. So we have to think of another reason, and the other reason is that the Hong-Ou-Mandel effect is only perfect when you have exactly one atom per beam. You can see this in this formula. If you only have one atom per beam, the probability GAA is probability to detect two particles. If you only have one, this is zero. And if this is zero and this is zero, you have one, the maximum visibility. But as soon as these quantities are non-zero, your visibility is lower because everything is positive here. And indeed, if we look at the region we are collecting data, we measure a mean atom number of 0.5. And this means that, yes, time to time we have 1 photon per beam, but we can have 2, and rarely, but it could happen, also 3. And this leads to this finite value of our visibility. So this leads me to the conclusion. What do we have learned? I won't say we have learned something on the theory of quantum mechanics, but that we have benchmarking our way to manipulate the atoms quantum mechanically, and benchmarking the quality of a source, that the modes we're dealing with are similar so that they can be made, the atoms can be made indistinguishable. The bad thing is that each point on this data, this is roughly 10 hours of integration time, and this is probably 20 or 30 hours. So it takes time to see this, because everything, I mean, you have a lot of other parameters to control, and so this is a bit painful. I also mentioned there is another experiment of that type published roughly 6 months earlier than us by the group here in this paper. So what will be the next? In my short list at the beginning, I mentioned a few experimental demonstrations. Amber, Bernard Twiss, Bernard Bagberg, Hongo and Mendel, but obviously one was missing, the violation of Bayes inequality. So this is our next goal. It will take even longer than this because it is even more complicated. It will take probably a few months. But we want to try. There is some numerical simulation made in this paper saying that this type of experiment could work. And we also envision another type of experiment that the Einstein's Positron-Rosen paradox can be translated in an inequality that you can violate. And this also has been simulated in this paper. And with this, I thank you for attention.